1.1 can change occur at an instant. You're probably wondering who these two people are right here. This guy on the left, his name is Newton. The guy here on the right, his name is Leibniz. So, who is the founder of calculus? There is controversy between these two who founded calculus. If you're interested in learning more about this debate, you can go to Google and Google it. On to the lesson. Question 1. Mr. Brust's distance from his house is modeled by the function d of t. While riding his bike to the store, he realizes he dropped his wallet and turns around to find it. After finding his wallet, he finishes his ride to the store. So to understand this graph, if you're tracing my cursor, I'm going to reread the parts of the problem. While he's riding his bike to the store, you see right here is riding his bike to the store. At this point, he realized he dropped his wallet and he's turning back around, going back towards his house in order to find it. He finds his wallet right here, and once he finds it, he continues his ride back to the store. You see at the 8-minute mark, he arrives at the store, which is a distance of 1,300 meters from his house. What is his average rate of change, or average speed, or rate of change for his trip to the store if he arrives after 8 minutes? So that's from the 0-minute mark to the 8-minute mark. You see the 0-minute mark, well, he's at a distance of 0 meters from his house. And then at 8 minutes, he is 1,300 meters from his house. So his average speed is just the slope of this line between these 2 points. So we had to find the slope of this line. If you recall from algebra, y2 minus y1 over x2 minus x1, that is your standard slope formula. And you can use this to find his average speed or rate of change. So to find the slope of this line, we just do d of 8 minus d of 0 all over 8 minus 0. And that's equal to, well, when t is equal to 8, d of 8 is 1,300. When d of 0, he's 0 meters away from his house, and then 8 minus 0 minutes on the bottom is just 8. And if we put this into the calculator, we get 162.5 meters per minute. That is the full calculation here. For parts B and C, I'm not going to do the full calculation. I'm just going to do the setup. So what was his average rate of change between 2 and 6 minutes? D of 6 minus D of 2 over 6 minus 2. What was his average rate of change between 2 and 3 minutes? D of 3 minus D of 2 all over 3 minus 2. So this next question here, is it possible to know how fast he was going at an instant? So these previous questions, we've been finding the rate of change between like 2 different time periods, like from the 2-minute mark to the 6-minute mark, from the 0-minute mark to the 8-minute mark. What if we just want to know how fast he was going at one point and not an average between 2 different times? So this is what we call, what we're looking for is called instantaneous rate of change. D. Give an example of how to calculate a rate of change that would give a close estimate to the instantaneous rate of change at t is equal to 2. So we can do this. Let me show you here. What we can do is pick 2 points that are really close together. So we did the 2-second mark and then the 1.999 second mark and did the slope formula there. So this is the rate of change, slope from between 2 points. But because these 2 points are so close together, that gives us an estimate of the instantaneous rate of change at t is equal to 2. So if we want to calculate the rough estimate, first thing we would do is draw a slope, draw the tangent line at t is equal to 2. So when t is equal to 2, you see the point on the graph is right here. And if you want to draw the tangent line, draw one curve that only touches that point on the curve once. Maybe roughly right there. Again, it's just an estimate. So this is a this is a tangent line at t is equal to 2 because it's a line that only touches d of t at this point here when t is equal to 2. So now to get the rough estimate, we can just find the slope of this line. It's just going to be an estimate. We can take two rough points here. We can say when t is equal to 0, this is roughly 900. And then when t is equal to 4, we have 1200 here. And we can use these 2 points here to estimate the slope, or the instantaneous rate of change at t is equal to 2. So here we do 1200 minus 900 over 4 minus 0. So see, we'll just use these 2 points and plug them in the slope formula. 4 comma 1200 right here, and then 0 comma 900. These 2 points gives us the rough estimate of the slope. Equals 300 over 4, which would give us approximately 75 meters per minute. So this answer could vary based on how you drew the estimate of the tangent line, and then also depending on what 2 points you picked. So if you got like a different answer, like that's totally fine, as long as it's somewhere close-ish to it. Question 2. B of t represents the buffalo population in the United States where t is measured in years since 1800. What does B of 90 represent? So see here, t is equal to 90. T is measured in years since 1800. So when t is 90, that means you're in 1890. And that just tells you the buffalo population at that time. So B of 90 is the buffalo population in the United States in 1890. What does B of 50 minus B of 0 over 50 minus 0 represent? If you recall, this is the average rate of change. So this represents the average rate of change of buffalo population between, so you see here t is 0, t is 50, but in the context of the problem, it's 1800 and 1850. So what does B of 32 minus B of 31.999 over 32 minus 31.999 represent? This just represents, you see these 2 points they picked are really, really close to each other. That gives us an estimate of the instantaneous rate of change of buffalo population in the United States. I'm just not going to write it for space issues. In when t is equal to 32, that means we're in the year 1832 right here.